All right, today we're going to tackle one of the biggest questions in the future of computing. And to do it, we're going to use a guide you might remember from when you were a kid, Swimmy, that brilliant little fish who taught his friends to swim together like one giant fish to scare off the big predators.
So let's dive right in. If a quantum computer is our big fish, how many little fish do we need? But before we get to the numbers, we have to understand the predators. Why on earth does our quantum fish need so much protection in the first place? Well, it all comes down to what it's made of.
You see, it all starts with the very heart of a quantum computer, its basic building block, which is just fundamentally different from the computers we use every single day.
And this is where things get really wild. A classical bit, the kind in your phone or laptop, is basically a light switch. It's on or it's off, a 1 or a 0. It's simple and it's super stable. But a qubit? Oh, a qubit is like a spinning coin. It can be both heads and tails, a 0 and a 1, all at the exact same time. This superposition is its superpower, but it's also its Achilles heel. It makes qubits unbelievably fragile.
That fragility has a name, and it's the main villain of our story, decoherence. Literally any interaction with the outside world, a tiny change in temperature, a stray magnetic field, even a little vibration, can knock that spinning coin over. It loses its quantumness and collapses into just a plain old bit, totally wrecking the calculation. You know, it's famously captured in that thought experiment with Schrödinger's very unlucky cat.
And here's the crucial part. You can't even look at a qubit while it's doing its thing without breaking it. Any information that leaks out into the environment, any observation, forces that beautiful quantum state to collapse. This is the predator. This is the big fish that's hunting our little qubits.
So this extreme sensitivity, this incredible vulnerability, it creates two massive, and I mean massive, roadblocks for anyone trying to build a quantum computer that's actually useful.
Okay, so think about this. In a normal computer, how do we protect data? We just make copies, right? We have backups. Well, the fundamental laws of quantum physics say, nope, you can't do that. The no-cloning theorem makes it impossible to create a perfect copy of a qubit. And on top of that, the errors aren't clean. It's not a simple flip from 0 to 1. They're these subtle, tiny drifts. They're analog, not digital. So they're incredibly hard to even notice, let alone fix. So, if you can't make backups and the errors are super sneaky, what do?
And that, right there, brings us full circle back to our story. If you can't make a single little fish stronger, what do? You get it to join a team. You build a bigger, smarter, stronger fish out of a whole bunch of them.
The solution, which was pioneered by the mathematician Peter Shor, is just as elegant as the story itself. Instead of trying to shield one impossibly fragile physical qubit, you use a whole bunch of them to encode a single, much more robust piece of information.
And here's how it works. It's actually brilliant. You take a whole group of physical qubits, that's our school of little fish, and you link them together with this bizarre, almost spooky property called entanglement. It basically makes them act as one single connected system. This team forms one logical qubit. That's our big fish. So now, if one of the little fish gets knocked off course by some noise, the rest of the team can actually sense it and work together to fix the error, all without losing the overall message. It's teamwork.
Which, of course, leads us right to the billion-dollar question we started with. To do the kind of math that could actually change the world, designing new drugs from scratch or cracking today's encryption, how many of these little swimmy fish do we really need? The answer is, well, you might want to sit down for this.
For something like running complex chemical simulations, stuff that's way beyond what even our best supercomputers can do today, the estimate is we'll need around 1 million physical qubits all working together in this error-correcting team. 1 million.
But what about the big one? The one everyone talks about, cracking the RSA encryption that keeps most of the internet safe. For that, hold on to your hats. The estimates just skyrocket. We might need a mind-boggling 20 million physical qubits.
This chart really just lays it all out, doesn't it? The bar on the left represents where we are today. These are the NISQ computers. That stands for Noisy Intermediate Scale Quantum. They have, a few hundred qubits. The bar on the right is the goal, a fully fault-tolerant machine. I mean, the gap is just enormous. It looks almost impossible. Unless, of course, there's a shortcut.
And this is where the plot thickens, because it turns out those huge numbers might not be the final answer, all thanks to a really clever trick that sounds like it came straight out of a sci-fi movie. It's literally called magic. You see, it turns out that some quantum calculations are way harder to protect from errors than others. The really complex ones that give these computers their power are also the most delicate. So, magic states are kind of like specialized, perfectly crafted tools. Scientists prepare these states separately in a really clean environment, and then they inject their special properties into the main calculation. It makes the hardest parts of the job way more reliable.
Now here is the absolute game changer. Making these magic states used to be incredibly expensive. You needed a huge factory of qubits just to produce them. But some very recent breakthroughs in how to cultivate these states are slashing that cost. The result? We might be able to get the same computing power with 10 times fewer qubits. All of a sudden, that giant school of fish doesn't have to be quite so giant after all.
Just look at how fast things are moving here. Back in 2019, Google said a supercomputer would need 10,000 years to do what their quantum chip did. By 2023, just 4 years later, that number was down to 47 years. And now, in 2024, these new ideas about magic states are completely rewriting the roadmap. The progress isn't just one step at a time, it's leaping forward.
So yeah, the numbers, millions of qubits, they still sound pretty daunting. But the speed of innovation is just incredible. The target is huge, but human ingenuity keeps finding these clever workarounds, these shortcuts, this literal magic to close the gap. And it really leaves you with a fascinating question. With breakthroughs like this, will the day our giant Quantum Swimmy is finally assembled and ready to go exploring arrive a whole lot sooner than any of us expect?